He has background in parabolic systems and also control. Now she has this very nice work on how to use kinetic theory for data science problems and vice versa. So he's going to talk about some new results on that.
Yeah. So thank you, Lee. Thank you all for coming. It's a great pleasure to be here. It was a long time ago that I was here before, and I'm very happy to be here, and I had already very nice discussion. Thank you also for that. Yeah, I'm invited now to a data science seminar. I do a lot of things on optimization and filtering, and I thought that this might maybe fit the data science aspect. And I want to talk about some methods which we have analyzed using a little bit of kinetic theory and maybe also modified them slightly in order to improve some of the things. And I hope that this as a topic could also interest you. And these are recent results with a couple of former PhD students and postdocs. One is now in Ferrara, Elisa, and Giacomo just started a postdoc with Lorenzo Pareschi in Edinburgh at RWTH, and Giuseppe Visconti is now in Sapienza. So for different parts, different people contributed to that. Since it's a data science seminar, I didn't know precisely what to expect. I started with some actually practical problems which we had in Aachen, and then I will show the methods we used. And I will show two methods which we not new methods, but where we contributed a little bit, and then I will also show the results on these two real applications. These are applications which are within the university, so it's not industrial applications, but they are somehow inspired by industrial applications from the engineering. And so the one thing what you see here on top is actually a classical inverse problem on imaging. So they, in the medical school, they are interested in fluorescence tomography. So these are materials which emit light, and the basic idea is that that with light emissions you can have a cheap way to to follow and see where the material which you want to deposit in the body, where it actually goes. So of course you can have other imaging technology which is more fancy, but this fluorescence tomography is based on light, so it's quite simple, cheap, and the idea is that this could support somehow operational procedures by live imaging. And so what they need to do is, so you see here a lot of casings, so the actual probe is inside here, which will somehow emit some light, and then you cannot see this, but this is a particular material which mimics part of the of a tissue of the human body. And so what they actually need is you have then observations from this tomography, and then you want to recover the location in principle of this material. And this you want to do fast and with reasonable accuracy and so on. And you can imagine that you have then imaging data and you want to recover the location. It's a very classical problem. Sometimes there's also the point that this would be time dependent if this material is transported along the blood flow, for example, but this we haven't looked at.
There is a problem. They say the online audience, they couldn't see the slides changing. So do you want to...
Okay. So how can I change this?
Please stop share and
yeah, maybe stop share and
yeah, I go. Sorry. Because I switched to the presenter mode after. What about now? Does it work?
yeah, you can go ahead. And,
no, it works.
Oh. I don't know. So they didn't respond immediately.
Your screen, right?
Yeah.
I can. Oh, yeah, I can see it. Yes, it's working on my screen.
Working?
Yes.
Okay. Let's do this. Okay. So I was talking about the first picture, which is essentially an imaging problem. And so what they want is essentially the location. So just coordinates, ideally also the shape, and of course the the intensity of the emission. And so this would be formulated as a classical inverse problem, and you would try to identify this. You have a lot of noise in the sense that these coefficients, so this is inside, of course, the tissue, though it emits light, then it's scattered and absorbed. And so depending on the tissue material, you have different absorption coefficients and so on, and those are not known, they are only known for very particular configurations. So essentially, this gives you a distorted image. So you have some noise on this problem. And so the true part of identifying this is how to deal with that. And I would say that this is somehow related to this data assimilation. And then if it's moving over time, clearly you have also the history and you want to, I don't know, progress it and resolve this quickly. The other thing is here there are the names given of this machine, but is a drilling problem, and this is an engineering setup. And the basic problem is that you have a workpiece and you want to drill to that, and the workpiece has, of course, heterogeneous material. So you need to identify a suitable force with which you move on this workpiece, and you need to do that 100 times. So there's heat up of the material, which makes this problem more complicated the second time you go in. And so the force you actually apply would be a time-dependent function which we're trying to recover, and they call this trending coefficients because they have some parametrization of the force they can apply, and they want to identify this. And there's some noise on the problem because they need, of course, to do measurements in order to understand if they now need to drill deeper or less deep or in which position. So they have a measurement device which generates some, you will see the data later, which generates noise. And so you try to identify this. In both cases, what was interesting to us is that, in both cases, we would like to have something which, I mean, for that, it might not be necessary for this setup which I show here, but maybe in the future, we want to have a setup which can run with the process. So here's, I think, clear. You get some data, you need to adjust the force, then you get new data, you need to adjust again. Here, in principle, if this material moves through your body, it should also be like this. So it's all forward simulations in some sense. On the other hand, both problems are essentially inverse problems. You get something, you want to identify certain material properties, or here certain forces. You have maybe a mathematical model which predicts how, if you have a fluorescence material there, how it somehow, how the light emits and goes through the media. So you have forward models, you want to do an optimization or an identification of this problem which runs along the process. So so we wanted to have optimization methods which could do this without having to predict too much in the future, so that we can also do that fast. And so the basic setup which we used is to say that in principle we have a forward model. Everything is here finite dimensional. We'll come to this aspect later. So you have some coefficients. This could be, think of the location and the intensity of this fluorescence material, the source of this material, or think of the force term. You have observations, and this is, I think, the classical setup for this inverse problem, plus noise, right? For the noise, in principle, you can have different assumptions, what kind of noise you have. And one approach to solve such a problem is to say that, okay, you solve this by identifying now the location by solving a minimization problem. What you would like to do is, sorry, this is the wrong E, but maybe take the expectation of this difference, maybe if you know something of on your noise, weighted with the covariance of this observations. So this could be casting this as an inverse problem, as an optimization. This inverse problem, you cast it as an optimization problem, and now you ask yourself, can I find this? Yeah. And you can do this now sequentially. You'll say you have a lot of measurements, maybe with the fluorescence, you get, for example, different wavelengths, you get at different times these measurements. With the milling, of course, time is natural, so this vector, so you can do this sequentially. So there will be an end appearing. In these problems we had before with the material, I mean, you have probably heard talks by Lee on kinetic theory. So this propagation of light in a material is a PDE, could be a high-dimensional PDE, but you can derive reduced models. So this G, you might have not only one forward model, but you might have a hierarchy of models which you would like to exploit, right? So for the first, if you think of this as an optimization problem, you want to solve this, the first gradient step, you might not need a very accurate estimation of your forward model, you just might need a general direction in which to descend. So you might resolve to an approximate model. Another thing is that the G might be non-differentiable. This was one thing with this milling. They had they had a forward model, and when you look more carefully, it turns out that this was essentially part of the model was a table lookup, which is not was not considered by me as a full mathematical model, but this leads to non-differentiability of this model. So if I look at this problem and would start naively, then I would say, okay, I take the gradient and descend in this direction. Might not be a very clever idea for this one. For this identification of the source, we actually introduced also a penalization term because we didn't want too many locations. We used a sparsity promoting term, so this was also the non-differential. So the point is that I'd like to have methods which can solve inverse problems reformulated as optimization problems, which can deal with this non-differentiability and possibly also with hierarchical models. Yeah, and one thing which is nice and which links to my prior expertise maybe a little bit is that there is now recently a lot of investigations on models which are based on particles. And so the idea is that so X is what you want to identify, right? So the X star is maybe the optimal point, the one which fits in some norm you measurements best. And to say that you have two approaches, so you throw in a lot of trial points, and then you have two things. What they can do, they can on the one side they can explore the domain, so randomly move around, and on the other they need to somehow reach a certain consensus in the sense that they need to find a common point which is somehow the best among them. And so this XD would be the best among them, or would be an average among them given the costs you have. The X star would be the optimal one, and you hope that by these two mechanisms, the movement towards one point, as well as the exploration, you eventually reach these X star. This is basic idea of particle methods for optimization. Everything is forward, right? So they just move forward. There's not necessarily a gradient involved. And what you hope is that essentially the mean of the particles eventually turn towards the solution of your minimization problem. And you would also like that they all concentrate. So the variance of the particles should also tend to zero. And then you would also have, of course, some guarantees that this actually works if you want to apply this, right? So we are asking for convergence and robustness. So this is, this could be an approach where we can handle these different things for reasons I will tell you in a minute. But for now, if you think of this, they communicate, they find the best among them, and they explore the space, so there's not necessarily gradients involved, and you can even take different hierarchical models into account. And I will give you two methods, or I want to discuss two methods, which are of this type. One method can be reformulated under a certain assumption using a gradient to better understand why it works. The other method not. One of them is Ensemble Kalman filtering. So this is so you see that the particles move in a deterministic way. They communicate through the covariance matrix, and it's written here as a gradient in order for you to see that there's actually some hope that this method would converge. But if you look later in the derivation, you see that the gradient does not appear explicitly. It's a trick to reformulate this like that, but the method effect is effectively gradient free. The other method is more in the spirit of what I just said. So you have a joint point. This was this red point xt before. The particles try to tend to this point. I have to explain how this is computed. And then there's an exploration. So you add some white noise with which they explore. And then there's a weight, which tells you if you should go rather to the consensus or to the best possible point at the moment, or if you should rather explore. And the critical question, of course, is here in this scheme, is then, can you give a guarantee or can you give assumptions on these two parameters so that the method converges? And I want to show you both in action. For the second method, the question is, how do we find this point, or what criteria should this point have? I mean, for the first is, if you could rewrite it in this way, you can think of this as a gradient descent, or if in functions with a gradient flow, so you would expect that the cost functional decreases along the trajectories of all of these particles. So you could imagine that you end up in a local minimum. Here it's not completely clear, because so far here you don't see the cost. And so the trick there is to use this what is called Laplace method. So there is the, or Laplace principle, there is the relation between the minimum of a function phi and somehow a weighted average of this phi with the exponential, which is of this type. So you see there's a parameter alpha, this should tend to infinity, and for alpha to infinity, the weighted average of the exponential of minus alpha times phi normalized tends to the minimum of phi. This is it's a known principle. It's not used so much in optimization for a reason I can already tell you now. The value of alpha, so this is a limiting result, right? So it only holds in the limit alpha to infinity. And clearly, if you implement, it's not so clear how you should choose alpha, and the performance of the method depends on alpha, and there's no theoretical estimate, unfortunately, only for particular functions, how to choose that alpha. But I will show you results which show that the second method actually works quite well, and you can choose this alpha also very, very high if you implement this in a correct way. But this is somehow where the cost functional enters, and you see that if you now say that you take the left-hand side and you say that you discretize this with particles, so you just replace the integral by essentially a sum over the averages of the particles, this could be a good candidate for the consensus or for the best point which you currently have. And to this one, you should drift. And now it's also clear, so what kind of method do we want to use to analyze this particle system? So far, I gave you just two different particle systems which would evolve. You know now how to compute that. You can, in principle, now implement this method and see if it works or not. Question is, how can we say something mathematical about these methods? And so one thing is that if you look at this formula, so there are two approximations. Clearly, I have to choose an alpha in order to make this feasible. And second, I need, of course, to discretize this with these particles. So what I would like to do is, of course, take as many particles as possible in order to get a good approximation. And so taking as many particles as possible means, in principle, looking at a kind of kinetic limit or a mean field limit. And so this will be the crucial thing which we will look at. So I want to not study the particle system, but I want to study the corresponding system for the mean field limit. And for this formula is maybe easier to see than for the full equation later. But you see this xi times the exponential, and now you introduce an empirical measure. So you say that instead of looking at the individual particles, I look at the probability density of these particles as a counting measure, and then I can rewrite this just like as an integral against the particle density. So this is a quantity which, in principle, depends now on this measure. And I hope to also rewrite, of course, this dynamics then as a forward dynamics or as a PDE for this empirical measure. And then I would like to study this PDE. This is somehow the basic idea. What about the other method? Do the same thing, because here what you have is you have an interaction term of these particles, but then all of these particles, they do gradient descent for the cost. So the more particles you have, the better you explore. There's another reason, which I will come later to, it's about regularization, which will also influence the way why we choose many particles. So in principle, we have these particle methods forward in time, essentially, to optimize, can be non-differentiable functions. We have an idea on how to choose a consensus point, but now we go to the kinetic limit in order to understand a little bit about these methods. So, core idea, again, is shown here for simple dynamics. So this is now a dynamics for which is called for opinion formation, or just taking means of the dynamics. So you have particles. You have particles which evolve here in a deterministic way with some initial data, and you want to understand what happens, or how can you describe the dynamics in the limit for large particle systems. And so what you would do is you would move from this individual description towards a probability density, and you would like to propagate this density. And what you see is that, of course, there is a time derivative corresponding to the time derivative of these individual particles. Here you see an averaging over the particle density. This turns out to be an average over the kinetic density. And so the F would be the limit of this mu for n to infinity. You would assume that these empirical measures for n to infinity converge to some probability density. And then you have essentially this limiting here. And here, this measure, the probability measure, lives in an Euclidean space, whereas these particles are in Lagrangian, right? All these particles move at their own speed. So what you get is, you get essentially the Euclidean derivative of f times the measure. So this is somehow a heuristic motivation why you can move from one of these descriptions to the other. If you want to make that rigorous, and can be also done for the particle systems before, then you would need to introduce a proper setting. So for example, if you are interested in this probability density, maybe you can do this in Wasserstein setting, and then you would show that essentially this system or this sequence of measures for n to infinity converge to a weak solution of this equation. Yeah, so now we want to do that for these two methods. We start with this consensus method. So we have this dynamics. It's a little more complicated than the one we had before. This is a consensus point. This is a normalization. Here's a noise. So what you would expect is, compared to this derivation here, this is a fully deterministic system. Now you have here an SDE system. So of course this translates to some diffusion term. So here you see in this PDE you only have transport. Now the white noise there gives you some diffusion. So this is a basic setup. What is maybe still important to note is, okay, you drift towards the consensus point. You have this exploration, which you turn off if you are at this point, because you hope that if alpha gets large, that this guy actually converges towards a true minimum. And once you are in the minimum, you don't want the particles to explore anymore. Okay. Then you can do, like I did on 2 slides ago, you can do this derivation for the empirical measure. And what you get is maybe not surprising. So you have an averaging term, just like the averaging I had before, where this x alpha is now the corresponding measure there, which depends on f. You have, it's now multi-d, before it was 1d, so you have the divergence of this guy as a transport term, and here you have the diffusion term. And so this is now the final equation. And for that one, you can now do the analysis and obtain the following result. This is not by us, we have other results, but I think this is clear. This is for that simplified situation, maybe more easy to explain. So what is interesting is that you have, so how does it work? So you look at the PDE and you try to do essentially an energy estimate, which tells you that this F concentrates to a delta, because you want that the mean of the particles concentrate at the minimum and the variance tends to 0. So this means that for this F, it should concentrate, it should go to a delta. So you need an energy estimate. And the question is, what are the assumptions you need? And what is interesting from an implementational point of view is this condition. So you see that the drift has to be stronger than the diffusion. And if you take, now there are two choices. This is the simplest choice for which there's a full proof. If you take the norm of x minus x alpha squared, then you see that in the diffusion, you need the dimension of the problem piece. If you would take, this is the isotropic case, if you would skip this square here and would have as a first dynamics, or not the norm of xi minus x alpha, but really xi minus x alpha, then you can lose this dimension dependence here. And this is also. So, but maybe the more important point is that the theory gives you a relation on how to choose these two parameters. The second important assumption why the mean field is maybe necessary is this assumption. So this says that the particles have to be chosen in such a way that that in the support of the initial distribution, the true minimum lies. That the true minimizer lies in the support of the initial distribution. It's a very strong assumption because the true minimum is precisely the one which you want to achieve with your method. But this is so far we have not been able to remove this assumption. So this means that in your initial distribution on the level, you need to be sure that the true minimizer is enclosed. So usually what people do is then they spread the particles for quite well, try to spread them among the domain, which can be very hard if these are. But then what you obtain is essentially a decay of this kind of energy. So this tells you that this is a true minimizer, that the variance of F decays for t to infinity exponentially fast. Here you see also the rate, which corresponds to the two coefficients you have. And this is a bound for the Wasserstein-2 distance, so you to the delta of the true minimizer. So you really get convergence. There's a small problem with this, or a small, so this has, I think, by now already appeared, but so formally you only get this up to a time t star. So you don't know that this actually tends to 0, but this is more technicality. We're still working, I think Massimo is still working on that to remove this. But principle is an energy decay estimate for this dynamics. So you have, for a particle method, without gradient information, you have convergence towards the true minimizer. Second assumption, which is missing here, is that the alpha should be sufficiently large. Yeah. Sorry, so I don't know why I didn't put it, but I told you that everything, no, it's here. For all alpha, then alpha 0. So, so as a mathematical algorithm is quite nice because it gives you really convergence of a particle method with not too many parameters actually to choose. The only thing what you don't know is the alpha. The other parameters you at least know the ratio of that. And of course, this is a condition which you cannot check a priori. Yeah, but it is a convergence proof for the particle method in the case of many particles. So this was known, right? And so what we wanted to do is, since we want to apply it to the two problems, and the problems is not unconstrained minimization, because you have of course the cost is the difference between what you predict. For example, for the fluorescence tomography, you predict a certain image on which you would observe when you give a certain source location, and you take the difference to the data and look at this difference. But there is a constraint, and the constraint is that if I give you a source location, there needs to be a forward model which computes then the intensity distribution. So in principle, and of course you have also not not complete freedom in choosing this location. It should be inside the probe, should have certain properties, should have a certain volume. So in principle, what we wanted to do is we wanted to have a particle method where the particles don't move freely, but where they are constrained to some set. And so the set could be a simple hypercube, or could be something which is given through the forward dynamics. So if you would write that in general, then you would say that, okay, you take a set M in RD, which has a certain, which is closed and where the measure of the boundary is. Okay. And then the question is what to do. And of course, the simplest way to now apply the previous result is to say, I don't care that this is a constraint, I just penalize this. And I penalize this now using exact penalization, which you usually don't do in optimization, because for exact penalization it's known that the penalty function needs to be non-differentiable in order that minimizing P with the penalty parameter beta leads to the same minimizers as minimizing the original problem. And therefore many people before used exact penalization, didn't use this exact penalization because it leads, you introduce essentially a non-differentiable function. For the particle method, this is not a problem because the function phi could anyway be non-differential in the first place, and we only have to use this Laplace principle, so I don't need any gradient. This is why we thought that this might be a nice combination. So still there's one other problem, is that this penalty parameter, you know that it's related to the dual norm of the constraints violation, so the norm of the multipliers at the original minimum. So you know that there's a finite value, but you cannot compute it because you don't know the minimum. So the big question here is not that we do the penalization, but the question is how do you now do a method which not only updates the particle position, but maybe also in a reasonable way this penalty parameter. You know that it will be finite eventually, but you don't know how large it is. And so we propose, and we can prove that this converges to the constraint minimizer in the mean field setting, the following. So what we do at every iteration, so we update the particles and we also update this penalty parameter beta in the following way. So you give yourself some tolerance, which eventually will decrease. And you check against the empirical measure how large is your violation of the constraint. And if this violation is small, then you further decrease this. If it's large, then you increase beta. And so the question is, does this give you the correct results in the sense that does this algorithm give you a finite beta, so that you only have a finite many number of times this? And the answer is yes, although you can prove under an assumption that what will happen is that the beta through the algorithm eventually reaches the beta bar. Under what assumptions? Essentially the same assumptions as for the unconstrained case. So we need that also we have mass around the true minimizer, and we have then a condition that the constraint violation will eventually be larger than this value. And if this is violated a couple of times, then the beta eventually will be increased up to this value beta bar. After that, it will will not increase any further because we have identified somehow the true penalty parameter. Sorry. And the typical simulation, so this is iteration of the method, would look like this. So it would increase. You would see that sometimes the constraint violation would decrease, then it reaches the final parameter, and at that point at least the constraint, this theta, would decrease so that you fulfill the constraints in a better way. For that you need, and we took as a penalization function, one which is non-differentiable, just the distance to the set M. Then once you are at this point where you have identified the good beta, then you can essentially apply the previous result, and you see that this method would converge to the true minimizer under the same assumptions as before. And it will not increase every time, as just said, it will only increase up to as long as this v is larger than this 2 theta k. So you get a feasible solution with a finite value of beta for this constraint problem in the non-differential case. So this combines now the minimization, the unconstrained minimization with the constraint minimization using this penalization. Another thing which was important in the second example was in this drilling problem. They wanted to have a certain force so that the material is reasonably well somehow drilled, but they also wanted a minimal cost of this process, and they wanted not, they didn't want to choose a weight between these two costs, so they would like to have a Pareto problem. So they would like to find, to solve this as a multi-objective problem. And so the multi-objective problem means that you have two cost functionals which you in principle want to minimize, like this, and then you would like to find somehow the front in which you cannot improve both of them simultaneously. And so in this picture, in the space of the cost function, this looks quite nice. In the search space, yeah, you don't know how this parameter looks. And we thought that one can maybe also use particle methods to solve this multi-objective problem by just adding to each particle somehow a value which would tell me which of these cost functionals essentially you would minimize. Usually what you do is, comes on the next slide, is called convexification. So you would combine all these cost functions into a one function with a certain parameter, and we would like to give this parameter also to the particle method so that each particle solves in some sense its own minimization problem. And if you look at a simulation in the search space or in the image space, you would see the particles which now somehow concentrate along the true minimizer on the search and on the particle space. So you would have a benefit in the sense that normally, if you would like to do that with classical optimization, you need to solve this problem for every these parameters. Here we would simultaneously solve for all parameters in one run. How does it work? You would add one thing I should say is that there's a lot of literature on what is, so there's weak Pareto and there's full Pareto and so on, optimality. I don't want to go into that, but if you would like to have equivalence of this problem to the minimization problem also in the weak sense, then this function which you generate out of the other cost functionals is also not differentiable. It's a max of all the other g's. So also in this case, a method which can deal with non-differentiable functions is probably useful. So what you can do is, of course, you can now just apply this. This is not very fancy. You can also do the mean field. You get just an additional parameter which is transported with these particles. I don't want to bother you with that. What you can get the same convergence result. What we were a little bit annoyed by is every particle solves its own minimization problem, which depends on this parameter W, which is chosen in the dynamics initially and fixed. And of course, you get, maybe if you do it equidistant, you get somehow this approximation of your Pareto front. And this is not nice because you are missing part of this Pareto front, right? You don't have any particle here. This is due to the fact that if you take equidistant W, it doesn't say anything on how good you approximate the final front. So we thought that maybe, since we have now this additional parameter, let's also do a dynamics in these weights. And what you could do is you could say that the weights, they should be such that these points push apart along this front. So you introduce a potential which essentially pushes these points. Here's maybe a better picture. You have a discretization in the weight space W, equidistant. You see that your Pareto front is poorly approximated. A better discretization would be that one. Here you have an equidistant discretization of the Pareto front. So what we said is that ideally you would like to maybe do it the following way. You change these W's dynamically at each iteration. and you introduce a potential, and this potential should push the points away in the W space. Based on the values in the space of the objective functions. So it's hard to see, but here this is a large gray area because these points are closed, so this potential is large. Here the potential is smaller because these points are more apart. So the dynamics would look like this. Instead of fixing initially just these weights and wait until this converges, you dynamically change it. You say you push it according to the difference in the image space with some potential, and I have different examples later. And then, of course, the weights need to be a convex combination, so you need to project. Then you can also do a mean field, and you can also analyze now what happens. So what you can analyze is, so what we would like to see is if this converges to the true minimizer. And so what we see is that since there is now also a dynamics in the weights, they are not allowed to change too quickly compared to the true dynamics. So before there was this relation between the noise level and the drift level, now you have an additional time scale, which is a time scale at which you change these weights. And under these assumptions, you can do this, you can prove this result. You can also show that the potential actually, once you are on the Pareto front, decreases. Yeah. So there's like an estimate here, which is only true for radial symmetric potentials. So again, point is maybe not these computations, but the point is that on the mean field level, we have now extended phase space, but we can show some nice convergence result for this situation using, I don't know, these PDE results. And then you ask, does it actually work? And this is, there's a big library of test problems for multi-objective optimization problems. And so there are two examples picked here. These examples are labeled and they're indexed by these K and S. I think the point is the following. So here you see it's a non-convex Pareto front in image space. You see different potentials. So this would be no potential. You see a lot of discretization points here. This is with the most potential, that looks nicer. You can also do that if the Pareto front is disconnected. You see a couple of these points also indicated here. They jump actually between things. So this is maybe not desirable, but I haven't fixed this yet. You see also here the weight distribution. So you see that it's far from. Yeah. And just to show this, you can also do this with 3 objective functions. Looks more fancy, but it's the same idea. So I will skip this. Then we apply this now to the fluorescence tomography. We also used I didn't show the equations, but what we have is radiative transfers with light transfer in absorbing and scattering media with different media coefficients for these different things. And so the blue is what they use right now, which is called SP1. This means that there is a diffusion approximation to the radiative transfer equation used. And it's known that this is not a very good choice if the medium is highly absorbent and not so much scattering. It's a very good choice if it scatters a lot, as one can imagine, because then the light is scattered in the tissue and then it behaves like a diffusion process. Instead of this SP1, you can use higher approximations to the radiative transfer. So you can go to 3 or 5, or I said this in the beginning, we don't have a theory for this, but in principle, you can also change, for each of these particles, you can change what kind of phi it actually should minimize. So, and what we said is that we do it adaptively. So we start initially with a phi which is an SP1 approximation to the radiative transfer equation, and then we increase this up to SP5, I think, with this method, as closer as we get to the minimum. Then they have the pictures of the phantom and the pictures of the recovered location. It's probably not very visible, but the point is that with the SP5, with this adaptive method, we were able, of course, to get a better location of the original source compared with the original algorithm. It's also displayed in these numbers. I only show this in order to convince you that we also actually solved the real problem, but with this particle method, right? And so here we had, and we did it with a particle method because we wanted to adaptively change essentially the solver, which would predict us from a given source how the intensity distribution is. Yeah, maybe I say a couple of things, but quickly on the second, on the second approach, because I think this is also related a little bit maybe to this, maybe people have seen this here already, so about this Kalman filtering. So Kalman filtering is a process for if you want, for variance reduction, and there's this ensemble Kalman filtering where you consider a large class of particles which actually propagate. The original method proposed looks like this. So you have data, you have your model evaluation, and you have a weighting term where the noise of the model enters, and where the convergence of the noise enters. You have a term which is the variance of the model evaluated on these particles, and you have this mixed term. And what is interesting about this method is that somehow you have a forward method to solve this problem. So as n goes further, you will get a point which essentially minimizes this norm difference z minus g of x in this weighted norm. And the question is, why don't I need any regularization in order to I don't know, to fix this or to get some good convergence results? And the answer is that somehow this method has an implicit regularization in the sense that all these iterates will lie in the convex hull of the initial particle distribution. So a little bit similar to this method I showed before. So this means that if I would like to look at this from a kinetic perspective, it would be highly desirable to take a lot of particles, because then I can cover, of course, a lot of ground. So we were asking, can we do a large particle limit and say something about this method? Again, if you look at this method, that's why I said one can rewrite it in different ways, but here no gradient appears. Okay. So the basic method is like this. You take the delta t to 0 limit, you get a system of ODEs. You can go from the system of ODEs only coupled mildly, not as strong as before, to the CX term, which is this term. This term can be written also using empirical measures. You can end up directly here. In order to see a little better what happens, and for the original, or for the convergence analysis, this is done by Andrew Stewart, he looked at the case where G is linear. If G is linear, then you can rewrite this in this nice way, where you have essentially a gradient descent with a certain matrix, which, if you look carefully, is positive definite, or which gives you a nice descent direction. And I think I missed a minus here, but yeah. And then you have this initial. Okay, so now what can you do with that? You can now, of course, discretize this again. If you use particles, you end up with your original method, but you could also use some other scheme, right? So you have here experts on Fourier, but you could also use any high order scheme, then this would give you a different method. We were looking at the moment system, because we were thinking that maybe it's enough to actually look at the mean and the variance of f. So you can derive a moment system. So you can just integrate this equation against x and x transposed, and you get an equation like that. In this case, if G is linear, you can also close this. So it will be an explicit system in N and E. And then you can look at the stability of this system. It's just an ODE system. And so what we were interested in is the question, is this stable at the desired minimum or at the expected minimum, namely at the point where the variance is 0 and m is just some number. And it turns out that this moment system is non-hyperbolic unstable. So this means that you might need to modify this, because it could be that you are on the boundary of this region, so that when you are close to the minimum, that this, because of numerical errors, you would move away. And so we then used somehow this moment system and the analysis to modify the scheme, and you could think of several things. You can add either here, for example, a small damping term, or you can add an actual regularization to beta on this side. And then you can do the same analysis and you get a stability region. So here, this was the original one for 2D problem. So along this line, you would expect your minimizers to lie, and there are these small gray arrows which show that this minimum, they would actually move away. And so with a modified method, you get that now this minimum is actually stable. Also works. There's, you can do now a couple of tests. This was a test which was in the original paper of Stuart on this method. So you have a PDE, you want to identify U given some noisy observations, and you can then reconstruct U and P and do that for the stable and unstable version. We also, you can do this in a constraint case. This I want to show because the method is, in principle, as I said, does not rely on the gradients. I have now used these gradients because I think this is easier to understand what happens, but in principle, it does not rely on this. And so we wanted to show this, and so we used a neural network, which is a non-differentiable activation function, stochastic gradient descent. You see the test error doesn't decay. You use the Ensemble Kalman filter, you see that you nicely decay. So it's this non-differentiability, if it's actually relevant, then as for your problem, you can do that. Still, the question is, if you do particles, these were a lot of particles for this neural network of this size, so of course it's also computationally expensive. This one is to say. And finally, because we also were able, I said that I wanted to show you the data. So this yellow is the data we observe, and so we did this now with a classical Kalman filtering, and so depending on what kind of drilling routine they use, alternating, ascending, and static, you see that in particular in this one, the predicted force difference is somehow way off, and it starts to oscillate. If you take the stabilized version, it somehow captures the trend a little better. So this is just to say that, okay, the other problem I showed, we actually also tackled together with these engineering colleagues, and that this stabilization made a difference for that particular problem. Even though we cannot prove that for this particular problem, we are really in this case where we are close to this non-hyperbolic unstable equilibrium. Okay, I think with this, I want to close, and thank you for your attention. I'm happy to take the questions you may have. Thank you.
Any questions from audience?
There's two questions. The first one is about the convergence result. Maybe back to the page around 10.
Yeah.
So in that the so-called global convergence result, just want to make sure if the minimizer X star is a priori known or not.
So normally it's not known, right?
Yeah.
Yes.
Before you do it, before you find it.
Yes. So it's not known.
But you know the existence of such a.
The existence. Well, the existence follows from just the assumption on continuity, for example, of phi on the compact domain. So yeah. So this doesn't say anything about the existence. So we always assume that there exists a global minimizer. The problem is that in this theorem, you need also to assume that your initial distribution has mass close to the global minimizer. Yeah.
A second question, maybe back in page 7. If you set up your dynamic system like the average of the
Yeah.
xj, right? So I didn't see the connection between this dynamic system back to your original.
No, this is just to illustrate how to do a mean field limit.
Okay,
Okay, so
it
this
has nothing to do with the.
Well, if you want, this is also an average, right?
Okay.
It's it's a weighted average, right? So this explains why in this term you have this guy here, which is the integral over x times.
Okay.
So this simple slide showed you that this drift term essentially reappears here. It's the same. I mean, it's the same thing except for the fact that here the average is also weighted. Yeah, but you are right. It has nothing to do. It's for. Yeah, some of you are very familiar maybe with these kinetic theories. For them, it's not surprising to get this kind of equation, but if not, then this would give you some idea. And here, this noise gives you then the diffusion, right? Yeah.
Any other?
Yes.
Question about the field dynamics. So the equilibrium measure is not given by the plot.
Yes.
So then. First, so does the PD has a unique equilibrium, and how fast the dynamics contract to the equilibrium?
So this is answered essentially by this result. So it goes exponentially fast towards the equilibrium. This is a positive quantity, right? And this is the variance around this x star. Unfortunately, this would be nice if you could prove that for all t up to infinity. So the proof here is only up to some given time t star. So the reason is that in the original proof there are further lemmas in order to estimate f, and some of these constants they depend on time explicitly. So there has to be a maximum time. So you cannot prove that it's a delta in the end, right? So there will always be a gap here.
So what if you run after the t star?
So analytically it's not known. Numerically, you see that it further concentrates. This is why I'm in contact with Massimo, and he believes that it's a technicality, but it's a serious technicality. Yeah? But numerically, there is no observation that the particles will move away from the minimum again. And and so the rate is essentially this one, right? So it's a relation between the drift and the diffusion, because you ask how fast this will decay, measured, of course, in this norm. I mean, it's maybe
But here you assume that you have one global minimum, but you can have a lot of local minimums, right?
Yes, but with the Laplace principle, if the alpha is sufficiently large, you will go to the global minimizer, because the Laplace principle will essentially, if you have a local minimizer, it will eventually be damped out by the value of the global minimizer if the alpha gets large. So you actually get to the global minimum. Yeah.
Any other questions?
But this is, so I must say this again, so this assumption is critical, right? So this one, if you start with the CBO method, with this method, with initialization, which is far from the true global minimizer, it will not move. But there are now ideas, I mean, you can change a lot of things, right? So you can maybe play with the noise, make it dynamically larger, and so on. So you can think of many variants of how to study this. So I showed only the constraint and the multi-objective, but it's an active field, right? So if somebody has another idea on how to balance these things, it's nice. And the PDE is, of course, degenerate, but only at the point which you are actually interested in. So it's not too bad in some sense. So it's, it could be something done maybe. Yeah.
Any other questions? If not, let's thank the speaker again.
Thank you. Should I stop now?
Yes.
Sure. So what will you do? Thank you. enough.